Okay, so as we just mentioned, energy cannot be created or destroyed. It can only be converted from one form into another. Now, this equation, percentage efficiency, what you can do, or what I encourage you to do, see if I can get Microsoft Word going here. Here will be your first little equation for your summary. And I'm not going to get too fancy with the equation editor. I'm just going to kind of write it out. I'll just write it out longhand, but I'm going to write H equals, make that a little bit bigger so you can see it. H equals E in, or no, E out over E in. And so on these guys, here's another thing I'd like you to do on your equations. Put them in a font with a serif, like Times New Roman. And another thing I'm going to need you to do on your equations is always italicize your variables. The way we know it's a variable, like you write the letter I, it's not, you're not talking about yourself, you're talking about current. And might also behoove you to learn a little bit of the Greek alphabet, because the Greek symbol for efficiency is eta. And if you take your H on your keyboard and turn it into a symbol, out pops the eta. Okay. Yeah, pretty handy. You can go like this. I put a speed key on my keyboard sometimes, but I do a shift left arrow, and then even hitting Control D will do it for you. You can see how simple. Control D in Word, or yeah, like you said, just go up to the font drop down. That'll work too. Now another thing, I'll do equals. On these subscripts, to toggle that, you hit Control equals or Control Shift plus if you want the superscript. And then what I'm going to do is this, copy, paste, Control C, Control V. Control I. So eta can either be the, and so you can either do it like right now, what's the efficiency right now if you're doing power, or what was the efficiency over the cycle of your drive or your engine. So if you add up all of the power consumption, you'll get energy, and you can think of the efficiency of, gosh, I mean, a good example would just be driving somewhere, right? So let's say you're going downhill, you take your foot off the accelerator, if you're in an electric car, like nothing's running, and so what's your miles per gallon? There's no gallon, there's no energy. Your efficiency is as high as it can get. You're not consuming anything, but over time, it's gonna take you some amount of energy to get to your destination. So that's kind of this first equation. For your efficiency over a long expanse. The power is just, what is it right now? What's my miles per gallon? What's my heat in the room compared to the amount of natural gas I burn? What's the ratio between the amount of electricity flowing out of my wind turbine and the amount of wind blowing past it? So they're both right, both useful. So that is efficiency, and it has no units, no dimensions. If I ask you a trick question, what are the units or dimensions of efficiency? The answer is 1 or none. It doesn't have any. Yeah. Okay. Hydro can be as high as 90% efficient. Very little of that mechanical energy turns into heat. Most of it goes right into electricity. Coal-fired power plant, sorry, 30 to 40%. Why is that? A couple of folks did not get this correct, so I'm just going to copy this, paste it, equals a T hot minus T cold over T hot. This is essentially Carnot's equation, and it says that the more efficient you want to be, the hotter you got to get. Now, these formulas are all in kelvins. So, for example, let's just do an automobile, for example. Copy, paste. What's atmospheric temperature in Kelvin about? Wild guess.
You mean like, as far as compared to like what it is right now, Celsius?
Yeah, like what's the like if I only knew Kelvin, I would have to tell you just like if we were in
Track 247?
273. Yeah,
273, okay.
it's like 300. Yeah, 300. Good ballpark. So all heat, well, most heat engines here on planet Earth, operate in the atmosphere, 300 Kelvin. And if you're running hotter, let's just say you get your engine up to 600 Kelvin, which actually is twice as hot. So if someone says, it was 1 degree outside yesterday and now it's 2, it's not twice as hot. It's like still really cold, or still really hot, however. So, I mean, this actually is an absolute measure of how hot or cold something is. So, and so you have to use the Kelvin scale to get thermal efficiency. And then T hot is your 600. And you can see at some point, you just can't get the machine any hotter because the metal's going to melt, right? You're going to melt your engine. You're going to melt your you're going to melt your gas-fired turbine. So you're always knocking on this higher and higher efficiency. But sorry, second law. That's as high as you can go. And even Steve Running, our own Nobel laureate, is like, why don't they just make those coal-fired power plants more efficient? Well, they literally are doing the very best they can. Because, most of these companies are not in it to lose. I mean, so if your competitor can make more electricity with less coal, they're doing better than you are. So that's where we are.
Maybe they're putting more effort into stamping out the competition and to actually improve on their own procedures.
Oh, you and your conspiracy theory. Maybe.
I didn't start with that.
So there's your efficiency from and you can do this for any conversion. We could do the same thing, for the light bulbs, for nuclear reactor, you name it. So that's efficiency. Okay. So the second law, and we will touch on the second law a little bit. Second law just says that S dot. You know what? You get the new laptop with the fanciest version of Word, and like the good old stuff doesn't work. Normally, what would happen? A little dot would appear over the S, which just means, well, I'll write it this way: D S dt is greater than 0. So this is entropy, and I will define this for you. This might be the last thing we do here today before I let you go. And so here, let me define that. Okay, so that's the second law. And it says that the change in entropy as we move through time is always greater than 0. Now, can you violate the second law locally? Yes, we're all doing it right now. As we speak, we are converting chemical energy in our bloodstream to occupy extraordinarily unlikely phases of matter. I'm standing up, coherent words are coming out of my mouth, there's all kinds of other junk running in the background, my organs are running, there's like little molecular motors all over the place, passing ions back and forth. It's a highly unlikely state of matter that we're in. Same thing with our whole civilization. Like who, what? Look, just go jump in a time machine. Like, how the heck did that happen? So we ourselves are very unlikely. So we are constantly fighting against and defying the second law. But over time, on average, you can't beat it. It's all so this entropy thing, and just to define it more clearly, entropy it's the change in heat over the change in temperature. So, for example, when my gasoline goes into my engine at some temperature, it's going to come in cold. It's going to come in cold, and it's going to go out. It's going to go out hot. And we can just even write that. So delta Q. So the change in thermal energy is going to be the heat capacity times the mass times the actually the change in temperature. We're not going to dive into this too much, but as gas goes through anything, car engine, water turbine, wind turbine, it's going to get a little hotter. Has to. And so that's the change in the thermal capacity of that fluid or structure. You divide that by whatever the high temperature and the low temperature, and that tells you how much more disorderly nature became. So that's entropy in a nutshell. Okay, so that's the second law. It also tells you in what direction chemical reactions are most likely to flow. So if you go and look up the work of Gibbs, Josiah Willard Gibbs was awarded the first PhD in engineering at Yale University in 1906. He basically married physics and chemistry together and said, I'm going to watch this reaction. If the entropy goes up, it's probably going to happen on its own, just sitting there. If you want it to run the other direction, you got to put some energy in. Okay.
Because the heat has to go somewhere.
Heat's always going to dissipate, yeah. Which is similar to the third law, which says you can never reach absolute zero, because like the harder you try to push all the heat away, everything else is hotter. It's going to come back at you. So 3 laws: can't win, can't break even, can't stop playing. I don't know who came up with that. It was good. Yeah. Okay. Well, that is about it. We covered 1.1, covered efficiency, covered force, energy, and power. This last little thing here, capacity factor, just means the what chunk of time the thing is running. So you might have a 10 kilowatt system. Like we used to have a 10 kilowatt wind turbine sitting over here in Hellgate. We're going to put it over at the new K3 brewery. The thing is not running at 10 kilowatts the entire time. In fact, rarely would it ever run at 10 kilowatts. Typically, it's kicking along at 1 or 2 or 0.
Definitely will this morning.
Yeah, capacity factor just says over an entire year. So let's just say it was, for example, running at 34%. That means you got a instead of a 10 kilowatt turbine, you got a 3.4 kilowatt turbine. Effectively, that's what that capacity factor means. Okay, well, thanks everybody. Good first lecture. See you here Thursday. Uh,
So I'm not yet actually registered for this
Oh,
class.